and welcome back to my YouTube channel. Today I'm going to be talking about stoichiometry, moles, and more. I'm going to focus on the concept of moles and how to use dimensional analysis, and I'm going to go over the four main types of stoichiometry problems that there are. So what is a mole? A mole is a number used to make measuring individual atoms and molecules easier to measure. It's defined by Avogadro's number, which is around 6.022 times 10 to the power of 23. And also, just a quick note, the mass of a mole of any element is located on most periodic tables. So why use moles? Moles are used to measure really small stuff, aka the atoms and molecules, because it's difficult to count atoms and molecules one by one, and we never end up doing that in any labs. So the number 6.022 times 10 to the power of 23 is used to measure them easily. And they got this number from the basis of a carbon-12 atom, whose molar mass is exactly 12 grams and has exactly 6.022 times 10 to the power of 23 atoms. And we use similar forms of measurement like this in day-to-day life. This is just a much larger number, so it's hard to think about, but we use similar forms like a dozen, a decade, a century, a yard, to simplify larger measurements. How are moles used? So for many calculations, you will need to convert from grams to moles or moles to grams, since chemicals react based on amount and not mass. An example of this is 1 mole of hydrogen reacts with 1 mole of chlorine to produce 2 moles of HCl. But if we think about this in terms of mass, it's 2 grams of hydrogen and 70 grams of chlorine, which yields the 2 moles of HCl. So although the masses of the two reactants vary greatly, neither one of the reactants is limiting. So this is a normal reaction. You don't have to worry about limiting reactants, but it could be if there wasn't enough moles of one or the other. And that's why stoichiometry, the method of measuring the amount and reactants of products, is used a lot. Converting to moles. Many stoichiometry problems are tricky, not because they're difficult to solve, but because they require many conversions. But the thing is that conversions follow the same structure. So once you get the hang of this, it's pretty easy to follow. So conversions always go from an old term to a new term. So basically, you want to multiply the old term by a conversion factor, which is where the new term is the numerator and the old term is the denominator, so that the old terms cancel out and we'll be left with the new term. So the important conversions for stoichiometry include grams to moles and moles to grams. And for both of these, you'll need the molar mass from the periodic table. So if you're going from grams to moles, you'll take the number of grams times 1 mole over the molar mass that you get from the periodic table. Then grams and grams will cancel out and you're left with moles of whatever substance. And if you're going from moles to grams, you start with the number of moles of a substance and multiply it by molar mass over 1 mole of that substance. And then moles and moles will cancel out and you're left with grams of that substance. Types of stoichiometry problems. For all stoichiometry problems, be sure that you have the correct balanced equation and know how to find the molar mass of each compound or element. That's the most important step, because if this is wrong, the rest of your problems are going to be wrong. There are 4 types of stoichiometry problems, 2 that involve a limiting reactant and the other 2 that don't. The ones that don't involve limiting reactants are the easiest, and usually it's just moles to moles or grams to moles, and you just need to use the mole ratio to convert from moles of a substance to another, or for the grams to moles, you need to use molar mass to convert from grams to moles, and then convert from moles of one substance to another. However, for the ones with limiting reactant, say for moles to moles, you need to test both reactants using the mole ratio and see which makes the least product. That'll be your limiting reactant, and that is the actual amount of product you can make, because you can't make more than what's available. Similarly, like grams to moles with a limiting reactant, You use the molar mass to convert from grams to moles. Then you test both of the reactants using the mole ratio to see which makes the least product, because you can't exceed the amount of moles available. These are hard to understand primarily because you can't identify the limiting reactant from the beginning, so you have to test both reactants, and your answer will always be whichever reactant gives you the least product. That's the key part to know about limiting reactant problems. And so these are your 4 types of stoichiometry problems. Sometimes problems might ask for the answer in grams, which is going to require one extra conversion at the end, going from moles to grams. Now on to examples of stoichiometry problems. Example number 1, mole to mole. How many moles of NH3 can be produced with 6 moles of hydrogen and unlimited nitrogen? So now you need to write the correct balanced equation and set up the conversion. And you know that you have unlimited nitrogen, which means what you have to worry about is your 6 moles of hydrogen. So you can start with 6 moles of hydrogen, and you know your answer has to be in moles of NH3. So your conversion factor is how much NH3 you can make per moles of hydrogen. So you can make 2 moles of NH3 for every 3 moles of hydrogen you use. So then you can just multiply this out using a calculator, and you will get 4 moles of NH3. Now on to grams to moles problems. So grams to mole problems are slightly more challenging than mole to mole problems because they require that extra step of converting from grams to moles and then using the mole ratio to find the amount of product. So for example, how many grams of sodium is required to produce 117 grams of NaCl if there is excess chlorine? Also notice how this problem is giving you the amount of product and asking you to find the amount of reactant. This is virtually same as the last problem, except you're just going from product to reactant instead of reactant to product. It can be confusing, but it's virtually the same. Now we can set up the conversion, starting with 117 grams of NaCl, and then converting to moles using the molar mass of NaCl. Then you convert from moles of NaCl to moles of sodium using the mole ratio of 2 to 2. And then since our question asks for us to provide the answer in grams of sodium, you have to convert back to grams using the molar mass of sodium, which gives you an answer of 46 grams of sodium. This is a good example of a test problem, especially because it asks for the amount of sodium in grams at the end, which typically people might forget or not notice when they read the problem and leave the answer in moles. And it's also a good example to show you that you can go from products to reactants and reactants to product. Now on to an example of mole-to-mole conversions with limiting reactants. So, for example, how many moles of iron 3 oxide can be made from 6 moles of iron and 4 moles of oxygen? So we can write the balanced equation for this and set up both conversions because we want to see which gives us the least product, and that will be the answer because we want to know which reactant is limiting, which will prevent more product from forming. So for example, we start with 4 moles of oxygen, and you use the conversion factor given by the mole ratio, 2 moles of iron 3 oxide over 3 moles of oxygen, which gives you approximately 2.7 moles of iron 3 oxide. Then you can go to the 6 moles of iron and multiply that by the conversion factor of 2 moles of iron 3 oxide over 4 moles of iron, which gives you 3 moles of iron 3 oxide. And notice how you have more iron and less oxygen. And so therefore, the iron is going to be left over because the oxygen runs out first. This means that O2 limits the amount of iron 3 oxide that can be made. So O2 is a limiting reactant, and the actual amount of product is 2.7 moles of iron 3 oxide. Now onto an example of grams to mole limiting reactant problems. These are the hardest problems, especially because you have to go from grams of each substance to moles and then set up both conversions and then compare to see which one is limiting. But if you're getting the hang of dimensional analysis, this should get easier over time. So for example, how many moles of water can be made from 8 grams of hydrogen and 43 grams of oxygen? And set up the balanced equation and notice that hydrogen and oxygen are both diatomic, so that's important to note. A lot of times people might forget this, and you need this both for the balanced equation and for the molar mass. Now we can set up the conversions. So if you're starting with 8 grams of hydrogen, you know that 1 mole of diatomic hydrogen is 2 grams, so you can set that conversion to convert to moles. And now you have to convert from moles of hydrogen to moles of water. And so we know our mole ratio is 2 to 2. And if you multiply that all out, you will get 4 moles of water. Now on to oxygen. You're starting with 43 grams of oxygen times the conversion to moles, which is diatomic again, so make sure you have the molar mass correct. And then you multiply by the molar ratio. Here it's 2 to 1. And then if you multiply that all out, you will get 2.69 moles of water. And this is the limiting reactant because it's less than 4 moles water. So you know that oxygen limits the amount of water that can be made, therefore it's the limiting reactant, and the actual amount of product is 2.69 moles of water. So those are all the types of stoichiometry problems. I hope you enjoyed this video, and please leave a like and subscribe for more.